Okay, well, thank you. I'm there. There's a message that Prasad normally provides, just in case there are any first timers on attending this presentation, first timer at the community of practice. So, of course, uh, we add our welcome to Pat's. Prasad is chair of Risk Informed Performance Based Principles and Policies Committee. I'm vice chair. The purpose of RP3C is to help modernize ANS standards. This was how it was put about 10 years ago when RP3C was started. It's working for the Standards Board, who decided back then that modernization would be good, and modernization has come to mean that risk-informed and performance-based methods are employed in standards to overcome the difficulties that we know about with purely deterministic and prescriptive methods. And then there's a little plug here for the Nuclear Energy Innovation and Modernization Act, in which Congress reinforced how it would be a good idea to increase risk-informed and performance-based approaches in this arena. There's a lot of guidance available for RIPV approaches, and we all know why. Because the conventional approaches have needed augmentation. But the thing is, these community of practice presentations are seen by RP3C as a very important vehicle for helping to accomplish this. Right now, ANS can be considered a knowledge center for RIPV information, with all these presentations on the RP3C webpage. As Pat will point out, many of them get a lot of hits, actually. Some of them are well attended, and many of them get a lot of hits. So, and there are good reasons for that, and I'm looking forward to this one. And with that, pleased to have here Andrew Whittaker to present, which I believe you can still see it on the screen. And he'll introduce himself, but I'm informed that his main credential is friend of Bob Budnick's. And with that, Andrew, please.
Thank you very much. And yes, my main credential is long-standing friend of Bob Budnick's. But to Pat and ANS, and I guess I'm a member of ANS, thank you for the opportunity to talk today. For me, this issue of commodification of advanced and micro reactors is becoming somewhat personal, in the sense that we need to find a path to net zero. Nuclear has to be front and center, and we have to enable this by perhaps moving nuclear from what has traditionally been considered boutique into a commodity item. So I want to talk a little today about commodification of advanced reactors and micro reactors, and from the perspective of a civil engineer who's invested in bringing about some change. So I am a member of the American Society of Civil Engineers. I learned last year I was a life member. I've been a member that long, and I'm a member of ANS. I serve as a SUNY Distinguished Professor at the University of Buffalo within the State University of New York system. And I've chaired for about 8 years now the Nuclear Standards Committee for the American Society of Civil Engineers. Now we'll see if we can get the technology to work. Here we go. So today, I'd like to talk with you about what I consider to be the 10 terawatt moonshot. I was young enough, I'm old enough, I should say, to remember man landing on the moon in 1969. And that was a tremendous achievement. I think achieving climate goals by 2050 is the moonshot of our generation. And that's the moonshot that those on this call and members of ANS can deliver on. And so I'll talk a little about that. how I think we ought to be commodifying nuclear energy, how we might rethink some external hazards and risk targets. And then I'll talk about the earthquake load case and seismic isolation, which is a topic I've worked on for a long time. And then if there's time at the end, I'll talk about a process or procedure to implement the commodification of advanced reactors in a program that's called Repower. So let's first talk about commodifying nuclear energy. How do we turn nuclear from something that everyone speaks about in hushed voice, that's considered boutique, into what a younger person might describe as a no, never mind. Just it's part of who we are and what we do. So what are some of the challenges? Clearly, nuclear is a great idea, but a question we have to address is cost. And so from my perspective as a civil engineer, what are the major impediments to deployment of new large light water reactors in the US? Clearly high overnight capital cost and levelized cost of energy. Now, I've placed LCOE in blue because there are different characterizations of levelized cost of energy. Another major impediment is the time required to deploy these reactors, large light water reactors, and the time to a return on investment. Importantly, there seems to be little to no learning from doing, which would enable us to achieve nth of a kind cost reductions. And I find the image bottom right to be particularly useful in terms of looking at cost. So this data, or these data, are taken from a study published in late 2018 that looked at capital cost of first of a kind plants and what we might be able to achieve with multiple units or perhaps nth of a kind construction. And there's a remarkable difference in first of a kind costs, or the cost of first of a kind plants, shown here in 2000, I think $17. Here in the US at $12,000 per kilowatt. Plant Vogel ended up costing substantially more than that. And looking at the costs associated with some of the builds abroad. Now, granted, there are different regulatory requirements abroad. Cost of material abroad is perhaps a little cheaper in some cases than costs in the US, but I think there's a remarkable difference here. So can we get to nth of a kind? Can we achieve the types of cost savings that we need to address this issue? Is nuclear just far too expensive? I believe we can do it. So if I step back and I look at the recent experience in the United States, and some of these numbers were assembled in concert with colleagues at Southern Company. If I look back at plant experience, and I try and break the whole process down into pre-construction and construction. The pre-construction activities spanned 8 years. They involved FEED studies that are listed here, ranging from geotechnical studies, probabilistic seismic hazard calculations, SSI analysis, scheme level design, design development, and then production of construction documents, internal and external events, PRA, and licensing. And this took more than 8 years. And then we move on to construction, which overlapped with some of the pre-construction activities, and there's a further 12 years. So more than 20 years to achieve a return on investment. And in discussions I've had with folks interested in nuclear, but not nuclear engineers, this seems to be a recipe for no commercial customers. One of the challenges that I'll talk about today is the seismic load case, which by and large makes every build nearly a first of a kind. So what can we do with the seismic load case to mitigate the impact, speed a design process? How can we turn this pre-construction work from 8+ years into 8+ months? How do we simplify construction and drive the construction time down from 12+ years to 24 to 36 months. There is our challenge. That's our opportunity. I'll note that the cost of civil and structural engineering works for large light water reactors is about 50% or more of the overnight capital cost. If we are to achieve the types of reductions that we need, namely reducing cost from about $14,000 per kilowatt electric down to about $2,500 kilowatt electric, we're going to need to achieve drastic reductions in time and cost, which starts with reducing the cost of the civil structural engineering works from where they are now by perhaps a factor of 4, a factor of 5. So how do we do that? I'll also note, and this is not news to anyone on this call, that while we can continue to build first-of-a-kind plants, we'll have no nuclear supply chain. So if we are to achieve an unprecedented build of nuclear structures in the US, namely moving from 2 a year to 50 to 100 per year, which will be needed to address the climate change challenges, we'll need an active, robust nuclear supply chain. And the point of reference I've been using for a price target for nuclear is somewhere between $2,000 and $3,000 per kilowatt electric, which is about a 5-fold reduction in cost from where we are now. So what are those next steps? I've found this paper published in Joule in 2020 to be an interesting way to look at the problem. And so with the theme of commodifying nuclear and changing the paradigm, this paper talks to issues related to design complexity and customization. And if I look at the lower left-hand part of the image, we have mass-produced products such as solar panels, LEDs, and similar. And these are not difficult to design, and they don't need customization. They can be reproduced anywhere in the world. So ready for mass production. And I look top right and I look at complex product systems, first and foremost, nuclear power plants. So highly customized and considered to be quite complex. So I think our challenge is to move nuclear from the top right in pink to the bottom left in yellow. If we can produce these mass-produced products, nuclear plants, then I think we can achieve our goals of this 10 terawatt moonshot, building hundreds and hundreds of plants becoming no neverminds, and moving away from the highly customized, considered complex process and product that we have now. So as I step back as the chair of the Nuclear Standards Committee, I look at our standards, and ASCE publishes ASCE Standard 4, publishes ASCE Standard 43. One deals with seismic analysis, the other deals with seismic design. We have a broad market in that these standards evolved out of DOE documents, and we're now looking to answer the question, how do we write these standards so they function well for DOE, that they serve as a basis for possible NRC licensing going forward. And then we recognize in nuclear power space that the world's changing, that as we write our standards, we have to keep in mind that we're no longer just dealing with large light water reactors, which I can tell you that in the last cycle of ASCE 4 and ASCE 43, in nuclear power space, that was our focus. But nowadays, in the last half dozen years, we have different thinking about nuclear energy. So top left, we have the Natrium build out of TerraPower and GEH. Bottom left, we have people thinking about marine nuclear for production of synthetic fuels. What role does ASCE have to play? We're not sure. But as we write our standards, we can't write rules that would prevent the deployment of nuclear offshore, recognising that nuclear infrastructure or maritime nuclear offshore has to be birthed every now and then. So we have a challenge to think through some of these issues. Now, I will note that NEI and EPRI are working with ANS, thinking about codes and standards for advanced reactors. And we are having a discussion about maritime nuclear and how does that all fit in. Then I move to micros, and this is construction at a scale that's fundamentally different from a large light water reactor. How do we write standards for something like the BWXT Pele microreactor or eVinci or the X-Energy microreactor? These are important considerations in the sense that we can write rules now and we can publish standards. The concern is that we do not want to hinder the development or deployment of any type of nuclear infrastructure. And bottom right is an image of what we're calling a hydrogen gigafactory. So this is nuclear infrastructure stood up specifically to provide process heat to then generate synthetic hydrogen at the scale that the country is now thinking about and looking to invest in. If we are to deploy or produce hydrogen at the scale everyone's talking about, nuclear has to be part of it. So as we write ASCE standards for new build nuclear, we just can't be thinking about large light water reactors. We have to think across this very broad spectrum of we write. It integrates nicely with work done by ASME and other SDOs. So we have to be sufficiently prescriptive so someone can follow the rules. We have to be sufficiently general so we don't stifle innovation. So we want to be part of the solution, not part of the problem. So let me move on from commodifying nuclear to a pet topic of mine. And I would encourage everyone to think about how we treat external hazards and risk. So I'll talk a little about risk-informed performance-based design. I'm an advocate for risk-informed performance-based design, but we have to ask ourselves the question, are we treating some of these external hazards appropriately? And are our risk targets sensible? I think it's time to revisit some of these risk targets for reasons that I'll describe in a moment. So I'm going to pick on a couple of load effects that I'm familiar with. And I'm going to preface my remarks by saying these external hazards and the risk targets we choose have an impact on cost. And I'm kind of laser focused on cost. And we have to also consider safety. And we have to look at safety not as nuclear alone, but in terms of other risks that we accept on a daily basis in society. So I am focused on cost, and I'm not going to relinquish safety one bit. I'm just looking to right-size our consideration of safety. So the three load effects I'll spend a few moments on are wind-borne missile impact, aircraft impact, and extreme ground shaking. And then I'll talk a little about acceptable risk, and that might trigger some discussion from those on the call. So those on the call may or may not be familiar with design of nuclear structures for wind-borne missiles. There are two regulatory guides that deal with this topic. One deals with tornadoes, one deals with hurricanes. And the genesis of these documents can be traced to work done at Sandia, funded by EPRI and other organisations in the 1970s. So the figure top right, taken from a publication by a colleague of mine and others on the call, John Stevenson, it reported on work done at Sandia in the mid-1970s on wind-borne missile impact, where telegraph poles, large diameter steel pipes and the like were projected into reinforced concrete panels with the goal of trying to understand how these panels behaved under such extreme loadings. That resulted in the writing of documents, including the regulatory guides, that again that date back to the late 70s and early 80s, where one considers the normal impact of a high velocity missile on a reinforced concrete target. So the most damaging of the missiles that are considered is a Schedule 40 steel pipe, 6 inches in diameter, about 15 feet long, weighing 130 kilograms, projected into impacting a panel at somewhere between 41 and 94 meters per second. And I'll just make the point here that the assumption of normal impact is simple, but it's generally wrong in that we have no evidence anywhere of such normal impact of such missiles on reinforced concrete targets. If I consider different angles of obliquity of the impact of the missile on the target, I have a very different outcome in terms of damage to the panel. So this is one area where we might think about right-sizing regulation, either to look at non-normal impacts or looking at the problem a little bit differently. But this consideration, in the absence of aircraft impact, will drive the thickness of a building envelope surrounding a reactor vessel. It just adds cost and, in my opinion, doesn't improve safety. Another important consideration, aircraft impact, that was a reaction to 9/11. And I'll note that I spent time at ground zero after 9/11, and it certainly impacted how I thought about building robustness and things of that nature. But I will just note here that the cost of dealing with aircraft impact on a nuclear structure is significant. And I will also note that aircraft cockpits in the United States and abroad, they've been secured for more than 20 years. There's no evidence, to my knowledge, of hijacking of commercial aircraft since 2001. And then the question is, could you strike a nuclear target, and why would you choose a nuclear target? So shown in the figures at the bottom, I have this stemmed from a discussion I had with colleagues about aircraft impact on a microreactor. And I must admit, I shook my head and said, how on earth would you hit it? And so drawn to scale is a Connex box in orange, and courtesy of Boeing, the 787 aircraft. And then the issue is, if you did hijack an aircraft, why would you pick a reinforced concrete box, not a political target? So if you assume that the aircraft can be hijacked and you wanted to hit a reinforced concrete box, could you hit it? And all of the evidence would suggest no. So I'd argue that the mean annual frequency of aircraft impact on a reinforced concrete box housing something like a microreactor is close to zero. And I will note importantly that the guaranteed fatalities from an aircraft strike or a miss is everyone on the aircraft. And that's not lost on me. So this is one topic I think we ought to be rethinking. And we don't design large commercial buildings for aircraft strike. We don't design political targets, let me call them, for aircraft strike. And so why are we designing civilian infrastructure for aircraft strike? Onto incredible ground shaking. And that is a a topic I'm well familiar with. I've worked in this space for a long, long time. And as we were working on a topical report I'll describe in a few moments, we looked to site an advanced reactor at Clinch River, the Oak Ridge National Lab. And if I somewhat arbitrarily assign this advanced reactor to seismic design category 4, which those involved in the writing of ANS 2.26 will be well familiar with, I've listed here levels of ground shaking that would be considered for design, and then more extreme levels of ground shaking that would be considered for risk assessment. And the two figures in the bottom and bottom right represent important information. So when one performs probabilistic seismic hazard assessment, one uses ground motion prediction equations and recorded data to develop what we call seismic hazard curves that are then turned into response spectra. Shown in the figure bottom middle is every piece of recorded data in Central and Eastern North America collected over about a 60-year period. And these data were used to develop the ground motion prediction equations for the Central and Eastern United States. This was work funded by the US Department of Energy, the US NRC, and the US Geological Survey. But the important point to note here is the scale on the y-axis. So of all of the records we have, and there are now more than 12,000, we have very few data points with high peak ground accelerations. And so the maximum ground acceleration here is of the order of 0.4 times gravity, and the ground motion duration for each of these records is relatively short. Now I move to bottom right. This figure presents design response shaking for seismic design category 4 at Clinch River. So design basis shaking for this seismic design category 4 reactor is more intense than every record we have collected across 3 million square miles going back 60 or 70 years. So I would describe this shaking at this particular site as incredible, not credible. Importantly, located a short distance from the Oak Ridge National Lab is Knoxville, Tennessee, not designed for any significant ground shaking. No facilities in that township will have been designed for levels of ground shaking that are remotely close to what I'd use for DRS for seismic design category 4 at Clinch River. Put differently, the city will not exist in its current form if it saw design basis shaking at Clinch River, for which we'd be typically assuming near elastic response in our nuclear structure. So we have to think a little about what are appropriate levels of ground shaking for design of nuclear structures. And if I'm performing risk assessment for this reactor at Clinch River, I would be considering multiples of ground shaking from 100% design basis through to perhaps 800% design basis. And I've seen these numbers presented at meetings and not necessarily well understood. But an important point to note here is that for about 1 million year ground shaking, or 1 million year return period ground shaking, that the horizontal accelerations the ground accelerations are more than 4G. And the important point to note here is that 4G horizontal means probably more than 3G vertical, which means you just launched your nuclear structure towards the moon. So in my opinion, as a civil structural engineer, we need to rethink how we represent ground motion and how perhaps we cap levels of ground shaking used for risk assessment based on recorded data in the United States and perhaps abroad from similar tectonic regimes. Moving on to tolerable risk. And I've had a series of discussions with folks, some folks on this call and others in ANS space about our QHOs, our quantitative health objectives, and perhaps the need to revisit them. And I'm just going to put some numbers out there for folks to think about. And I think it's important that we have this discussion about what is acceptable risk. So I just assembled some numbers here for the purpose of really trying to benchmark what society might accept in terms of risk. So your mean annual frequency of dying in a car accident in the coming 12 months is about 1 times 10 to the minus 4. The mean annual frequency of a modern building collapsing due to earthquake shaking is 2 times 10 to the minus 4. And if a building collapses, by and large, everyone inside will die. The mean annual frequency of death due to dam failure is somewhere between 1 times 10 to the minus 4 and 1 times 10 to the minus 5. And so these risks are substantially smaller by orders of magnitude than the risks we routinely consider or the risk numbers we routinely consider for design of nuclear energy facilities. So it's my opinion that now is the time to revisit risk targets for nuclear structures. A point of reference here, known to everyone tuned in today, and that is that we saw wholesale destruction of reactors at Fukushima Daiichi 12 years ago. No one died because of radiation poisoning. More than 20,000 died due to the tsunami. So we have very little data, but the data we have doesn't necessarily support the risk numbers that we're currently working with. So as we look to commodify advanced reactors and microreactors, I think we really need to revisit these risk targets and the QHOs. So let me move on and talk about the earthquake load case and seismic isolation. And it's my opinion that as we treat earthquake shaking at present, it means that every nuclear build is a first of a kind. And so how do we right-size this problem? Well, I just note for those unfamiliar with the earthquake load case that seismic hazard varies by proximity to a fault, local soil conditions, and seismic hazard is routinely characterized for nuclear applications through a shack process. One routinely considers soil structure interaction, which I think is a nuclear cottage industry, and I'll explain why in a few moments. It considers the coupled dynamics of soil and structure, and I think we need to rethink the need for SSI analysis. And I'll note that for deeply embedded structures, as shown in the bottom right by that blue buried structure, there is no way around not doing SSI analysis. For the surface-mounted structure in green, figure bottom right, I think there's a discussion we need to have on, is it really needed? Because adding SSI analysis to a design work stream for a new build nuclear structure, by and large, adds 2 years to the design exercise. And if we can shave 2 years off a design process because it's not really needed, that leads to a significant reduction in cost, a significant reduction in financial risk. So I think SSI analysis provides some really unique challenges. So in the figure in the middle, bottom right, in the middle right, I have a cross-section through the Hanford site, which is at one point home to more nuclear reactors, I believe. But the logic cross-section here is quite complex. But for the purpose of SSI analysis, if it's needed, that complex stratigraphy is translated into a horizontally layered site, such as that shown bottom right. And then we make the assumption that we have vertically propagating shear waves from a rock horizon at some significant depth, propagating vertically into our nuclear structure. Well, I can tell you that for the Hanford site, it's highly likely that surface waves, not body waves, drive the seismic hazard. That the seismic shaking that a building might experience at Hanford will be composed of surface waves and body waves. They will unlikely be vertically propagating body waves. They'll more likely be inclined body waves propagating up to the surface. So we make a series of assumptions for our SSI analysis that aren't backstopped by data. In fact, we have no real evidence that vertically propagating shear waves are found routinely as a result of large magnitude shaking. So we've made assumptions, and we made assumptions of vertically propagating shear waves starting in the 1970s. That was work at Berkeley, where I was a PhD student in the 80s, because that's what we knew then. And I think we know more now. So I think it's time to move on and rethink this issue of SSI analysis for surface-mounted structures. So how does seismic isolation play into all of this? Well, shown here is, top right is a cross-section through a seismically isolated waste storage facility that was planned for the UK and not built. And the seismic isolators are placed between the base mat below the spent fuel packages inside the building and above a foundation that is shown hatched. And these isolators have, in the United States, been vertically stiff and horizontally flexible elements, but nowadays we're considering a broader range of seismic devices for possible applications to advanced reactors. But long story short, these isolators serve to mitigate the effects of high frequency, high amplitude ground shaking. And the figure in middle right with the y-axis label of acceleration is intended to illustrate the benefits of adding a horizontally flexible element or elements beneath a stiff nuclear structure, where we shift or we alter the dynamics of the supported structure through the addition of these horizontally flexible elements. So you can look at acceleration here, spectral acceleration here, as a measure of force that you must design the structure for or the equipment for, put differently, cost. So the goal of the isolation system here, in my opinion, is to drive down force and drive down cost. And I will note that this is a technology that is not new. This has been used in the United States since 1979, where we had the first application of seismic isolation to some mission-critical equipment in Southern California. But the figure here, or the slide here, is meant to illustrate the breadth of application. So figure top right is a Sakhalin gas platform built off the coast of Russia in the very early 2000s. The isolators used for this particular facility are each rated to 17,500 metric tons. The same type of isolator at a very small scale was used to isolate the statue bottom right. This is the statue of Hermes, now at Mount Olympus. And the isolators here, identical in geometry, but scaled to Sakhalin. These were rated to 500 kilograms each. So 17,500 metric tons per isolator, 500 kilograms per isolator. I'd argue that the article that's isolated bottom right is more valuable than the article isolated top right. But other applications, most dating from the last millennium, the San Francisco International Airport under construction, the San Francisco City Hall, isolated after the Loma Prieta earthquake, an LNG facility, that's the figure at the bottom middle. These are friction pendulum isolators installed at Revithousa in the 1990s. A British Trident submarine, seismically isolated while in dry dock at HMS Devonport at Plymouth. A Department of Defense radar facility in Alaska. And bottom left is a hospital in Southern California perched right on top of the San Andreas Fault. So a broad spectrum of applications. And there are two nuclear power plants that are seismically isolated. One's in Cruas in France, the other's in Coburg in South Africa. And these were isolated using a technology that would not be used nowadays in the United States, namely synthetic rubber bearings. But a point to note here is that this is a technology that is not new. It has been widely used in the US and abroad. The number of applications in total is more than 12,000 applications of the technology worldwide. So as we think a little about seismic isolation and technology readiness, I think it's important to pause and say, well, what has been done in the United States to support the deployment of seismic isolation for nuclear structures? And there's a list shown here. These are projects I've been involved with. There are no doubt others. But the takeaway here is that there has been a significant investment in seismic isolation technology and considerations of applications to nuclear structures going back to the mid-2000s, starting with work funded by the US NRC and led by Dr. Budnitz, through to a topical report that I'll touch on that is about to be submitted to the US NRC, and two ongoing projects, one that's being led by my nuclear colleagues at MIT on a horizontally configured high-temperature gas reactor that will be seismically isolated, and a project now underway looking at the gamma irradiation of seismic protective devices. This is a project where work is being done at the Idaho National Lab. So sticking with technology readiness for a moment, I think we all know that one of the challenges at Plant Vogel was steel plate composite construction was deployed, and in hindsight, it wasn't technology ready. It might be technology ready now, but it wasn't back when Plant Vogel construction started. This was not lost on us. And so we've worked hard to provide a pathway to deploy the technology through codes and standards. So we have our standards, our ASCE standards 416 and 4319, dealing with analysis and design respectively. Each document has a chapter devoted to seismic isolation. And the strategies deployed in those ASCE standards map to target performance goals presented in ANS 2.26. Then we have three US NRC new regs on technical considerations for seismic isolation of nuclear facilities, but this focused on large light water reactors. And then we have companion documents also developed with funding from the US NRC on seismic isolation of large light water reactors using elastomeric bearings and sliding bearings. Last but not least, we have the report that Southern will deliver to the US NRC shortly that looks at guidance to implement seismic base isolation for advanced nuclear reactors, although I'll note here that the approaches that we're presenting in this topical report are equally applicable to micros and large light water reactors. So why isolate? And part of the reason is I'd like to be able to standardize nuclear structures, take the seismic load case, I won't say out of the design equation, but mitigate its effect on the design equation. I would like to move nuclear power plants from top right in the figure I introduced a few slides back to bottom left. So move nuclear to mass-produced products. So the figure at the just under the heading looks at what we do now and why I think it's a recipe for getting nowhere. Namely, the traditional approach has been design a heat source and assign a power rating, conduct a feed study, do design development, generate construction drawings, and then we construct. But it's a matter of develop a heat source with no customer. And I'm not sure that's a particularly robust model. And I think isolation can help change this. So you might ask, well, when was the first work done on seismic isolation of nuclear structures? In the United States, I can trace it back to work done in the late 1980s and the early 1990s, led by Professor Jim Kelly at the University of California, Berkeley, just down the hill from Lawrence Berkeley National Lab. And back then, GE was developing a design for what was known as the Advanced Liquid Metal Reactor. And GE early on determined that this reactor could not be built in regions of moderate to high seismic hazard because of the need for a thin-walled vessel. As soon as the wall thickness increased beyond a threshold amount, thermal gradients made the construction impossible. And GE concluded that isolation was the only pathway to building these reactors at many sites across the United States. So our history with isolation of equipment reactor vessels indeed dates back nearly 40 years to when I was a graduate student at Berkeley, and I witnessed these experiments as a graduate student. So I think we need to standardise nuclear structures to achieve the cost reductions I identified earlier. Seismic isolation can be used to take a standardised design of a building and deploy it anywhere in the United States, including the US territories. If we can get to standardised approaches, standardised designs, then we can think a little about how do non-nuclear sectors go about building these mass-produced structures. And they start to think about productized buildings designed for manufacturing and assembly. So these are cookie-cutter buildings, designed once, built many times. I think about standardization and the use of commercial off-the-shelf equipment, which becomes possible because the seismic demands on a lot of equipment inside an isolated nuclear structure are really very small. We separate the nuclear island from the balance of plant, and Natrium has done that. I think this is a pathway to the finish line. I would argue that in nearly all cases, if we're dealing with surface-mounted structures, we should be making use of the USGS web-based ground motion calculator, eliminating the need for a lot of probabilistic seismic, site-specific probabilistic seismic hazard calculations. I will note that this web-based ground motion calculator is used for mission-critical infrastructure across the US and has been used in this capacity for nearly 20 years. And if we can standardise buildings and standardise isolation systems, I think we have an opportunity, I should say, for one-time licensing of building equipment and isolation systems, enabling a robust nuclear supply chain. Now, one issue that came up a number of years ago was the cost savings. How can we quantify them? And we went through an exercise with work funded by EPRI and DOE to try and characterise the benefits of standardisation and on the cost of equipment. And without going into all of the details here, we see that for my two example pieces of equipment, in one of two buildings that we considered, we can achieve cost reductions in equipment if we think about a factor of 5. And here we're comparing first-of-a-kind conventional cost, or first-of-a-kind cost of equipment conventionally founded through nth-of-a-kind equipment attached to standardised plants if seismically isolated. So we don't have crisp cost data on reactor vessels and steam generators because they haven't been fabricated yet. But the data we did collect and the domain experts we did poll gave us high confidence that if we can get to standardised plants enabled by seismic isolation, we can achieve the cost reductions that we need to make nuclear viable. Let me just touch on a topical report that's about to be submitted to the USNRC. Southern Company is the lead for this particular project, and we're going to touch on all of the topics in the topical report, not today, that are listed here on the screen. But because we're talking about risk-informed performance-based design, I thought I'd touch on one important component of this topical report, namely a risk-based design of seismic isolation systems. This hasn't been done before, but it's actually rather straightforward. And so we're going one step beyond risk-informed design. This is explicit risk-based design of seismic isolation systems. And the topical report, which will also be published as an MCA report available for download from the University of Buffalo website, will lay this process out in some significant detail. But the topical report is intended to provide a roadmap for an applicant to design a seismic isolation system. So the goal of submitting this topical report is that the NRC will review it and endorse certain parts of it. But long story short, we take seismic hazard data and transform that seismic hazard data into what we're calling seismic displacement demand curves, which are isolation system specific. But the process is straightforward. With those seismic displacement demand curves, we then utilize an isolation system fragility function, and where that fragility function is developed using process and procedure that the NRC has seen now for many years, but just applied to as a seismic isolation system, not more conventional nuclear infrastructure. But with the displacement demand curve that we generate from our seismic hazard curves, we integrate that with a fragility function, we can achieve a target performance goal. So the computational process is straightforward. The development of the fragility function is straightforward, and we establish isolation system capacity by prototype testing, dynamic testing to large displacements at high velocities of seismic isolators. So the important point to note here for those that aren't civil engineers is that in seismic isolation space, we would test our isolators to demonstrate capacity associated with the target performance goal, and that we test every production isolator delivered to the job site for design basis demands. So these will be the most rigorously evaluated parts of a nuclear structure. So where do I want to land with all of this? Ideally, we end up with licensed design spaces for advanced reactors. And we've been working with colleagues at MIT on how we do this. We have pre-licensed seismic isolation systems with different capacities developed for different advanced reactors that by and large enable the speedy design of a nuclear structure. So if we have a pre-licensed building, we have as it characterized by the USGS ground motion calculator, we can basically select for a given site in a given soil condition a seismic isolation system that delivers the requisite performance. So my process, or the process I'd like to see, is that spelt out at the bottom of the slide. Namely, you pick a site, you pick a licensed heat source, pick your type of reactor and its power rating, you pick a licensed isolation solution, and you price the time and the construction for your particular application. And then you go through this process, you evaluate alternatives, you iterate until you have a design solution. But the goal here is to chisel down the design time from 8+ years to realistically, it doesn't need to be anything more than 8 weeks. And in doing so, I'm putting civil engineers out of business. I understand that. But that's the price we pay to deliver new built nuclear at the scale that I think we need to deliver it at to achieve climate targets. So with that, I'll finish. I have a long list of people to thank because many have contributed to the writing of these documents and the building of the intellectual basis for deploying the technology. So I have colleagues at the University of Buffalo and at MIT. I serve on the board of directors of a climate non-profit, Terra Praxis, and they have contributed in a very meaningful way to a number of projects that we've worked on. Colleagues working on standardised buildings and in London, Brighton Wood, work funded by the US Department of Energy, the US NRC, and the US Advanced Research Project Agency Energy as part of DOE. Lawrence Berkeley National Lab and Dr. Bob Budnitz, who's on the call. He deserves a big round of applause for where we've managed to get to now through council, knowledge of topic, and knowledge of many topics. Colleagues at the Idaho National Lab, EPRI, Southern Company, and we've done a lot of work in the last couple of years with reactor developers, wanting to make sure that what we do helps them innovate. It doesn't stifle innovation. So some of the folks who we've been working with are listed here, including Kairos Power, X Energy, TerraPower, Boston Atomics, and BWXT Rolls-Royce. So with that, I will finish. I'd be happy to take any questions. I think Pat is going to post the PDF. I'd be happy to take questions, and if you're interested in a lot of bedtime reading, I can put a series of publications up into a Dropbox or a box drive that you can download at your pleasure. So thank you for the opportunity to talk with you today.
Thank you very much, Andrew. We just have one little note in the chat box, and really just back to you, acknowledging you for all your work on the seismic isolation project that was funded through NRC. And of course, Bob wanted to make sure that everyone knew that you really pulled the weight on that one. So
yeah, can I just stop here? This is Bob Budnitz through and through. What Bob is trying to be is generous. I'm going to fault him that he said did nothing. With all due respect to my friend, that's nonsense. Bob and the other members of the peer review panel, including Bob Kennedy, Nilesh Chokshi, and others, they made and Annie Camera, they made tremendous contributions to that early work. They helped frame it. Granted, I was lucky enough to work with students, but they represented a tremendous sounding board. If we started to get off track, we were brought quickly back to heel. And so we owe Bob Budnitz a huge vote of thanks. And the one person that perhaps is not here today is Bob Kennedy, who passed away a number of years ago. Bob was tremendously influential as well.
Thank you. We do have a question from Frank Hope. And then he has said, is there an optimal size footprint for seismic isolation? Would this help large light water reactor costs similar to small modular reactors?
So there's no optimal footprint for seismic isolation. I think the point I was trying to make with the applications to date, the gas platform, where the isolators had a metre of displacement capacity rated to 17,500 metric tonnes each, to the statue designed at about the same time, where the isolators they still had significant displacement capacity, but they were rated to a load that was a couple of hundred kilograms. So these isolators scale. So you can isolate a diesel generator, you can isolate a cabinet, and you can isolate a large light water reactor. So the reactors that are isolated using the French technology, the Cruas and Coburg, they're large light water reactors. So could we achieve the cost savings? I think we could. But again, we built two AP1000s not we, Southern Company and others built AP1000s at Plant Vogel. They're first of kind. And if we build a lot more of them, could we build them far cheaper? Yes. If we could get rid of aircraft impact, would that reduce the cost? Absolutely. So I think the answer is no, there's no optimal size. Would the technology help? Yes. And indeed, Westinghouse looked at isolation for AP1000 15 years ago and got it to a certain point, and I think there were enough challenges with Plant Vogel and finishing that project that the technology wasn't pursued. But would it work? Absolutely.
Thank you, Andrew. Bob, we are just after 4 o'clock. What are your thoughts about ending promptly and taking questions by email, or what is your preference?
Well, first of all, I really enjoyed that. Thank you. Second, please carry out your threat or your offer to put bedtime reading in a box folder somewhere, and maybe Patricia can I don't know, offer a standard optimal way to do that. And then I realize we're a little over time, but I would cheerfully listen to people ask questions and have Andrew answer them. Hello?
Again, I'm happy to respond to email, jump on a telephone call. I'm passionate about this topic, as you might have guessed.
Yeah.
And I don't want to put civil engineers out of business, but I really want to right-size nuclear. So my real goal, and Bob Budnitz knows this, is I want to turn nuclear into this, just a cell phone. You decide, you go to the store and say, I want one of these and one of those, and pick what attributes you want, and then walk out of the store with your product. So if we can get nuclear to that point, we can build 10 terawatts of capacity. We can't get there if we spend 20 years designing and building the blessed things. We won't have any customers. But if we can make nuclear truly commercially viable, wouldn't that be great?
Agreed. And we appreciate your passion on this and your presentation. I think that we probably covered the questions, and I certainly appreciate, like Bob, that you're offering to put some additional files in a Dropbox. I'm happy to share that. Anyone on this community of practice that would like that information can contact me, or if they think of any questions afterwards, please do. I will share that Dropbox with the entire standards committee when I do send out all of the other information, so you'll get it there as well. But if there's anything else you need, just reach out to me. I want to thank everyone for joining us today on a nice Friday afternoon, and of course, particularly our presenter today.
Pat Schroeder, this is Bob Budnitz. My name got mentioned several times by Andrew, and I just want to clarify something. And I put it in the chat.
Yeah.
The project came to me at the Lawrence Berkeley National Laboratory, and I sent it to Andrew. And if you want to know what the division of technical work was, it was sort of 97 and 3 or something like that.
Yeah, I did more than 3%, Bob.
Well, I'm not going to argue the case, but I want to make a technical point. That is, if a designer or an owner of a facility wants to install seismic isolation, the first and most important question that they have to ask themselves is they have to develop an acceptance criterion for how much residual risk is still okay. Because without that, you can't design that system optimally, and with it, you can. And that turns out to be a barrier in some areas where the people don't even think about what the acceptance criterion is for a civil engineering design. Because nothing's perfect. There's always going to be some probability, which we struggle to work out, as to the likelihood that it's going to actually work under the loads that are contemplated or bigger loads than that. So that's an important area of thinking. And one of the things in the LBL project that went on for a decade, one of the things that went on there was an advisory review committee. Andrew mentioned some of them. There was, besides Bob Kennedy, and there was Don Moore from Southern Company, and there was Antonio Godoy and Andy Whittaker from the Annie Cameron from the NRC, and Jim Johnson and others. Is that we thought through with Andrew a way to formulate a sensible series of acceptance criteria depending on what you wanted. And that turned out to be a very, very sensible contribution. I want to urge people to read those reports that Andrew has published that has, and an NRC new reg also, that describe some of that. That's an important attribute. Thank you.
Thank you, Bob. Anyone else? Okay, I'll go ahead and end and leave you to enjoy your weekend. Thank you all very much.
Thank you.
Thank you, Pat.
Bye-bye.